Velcro strips are attached to two cards. This card has mass m traveling to the right at speed 3v0, and that card has mass 2m traveling to the left at speed v0. They collide and they stick together. Plot momentum as a function of time graph for each card and for the two-card system. And the velocity as function of time graph for each card and for the center of mass of the two-card system. Let to the right be the positive direction. First, let's find the card's velocity after the collision. It's a collision problem, so we can use the conservation of momentum. Initially, both cards have momentum, and the momentum is mass times the velocity m times 3v0 plus 2m times its velocity. Because it's in the negative direction, we have to say the velocity is negative v0. Afterwards, they stick together, so we have altogether m plus 2m moving at the same final velocity. We have 3m times v0 and minus 2m times v0. So 3 minus 2, we get 1m times v0. And then on this side, I have 3m times vf. So vf is 1/3 v0. It's positive, that means it's to the right. Let's start with the 1m. Before the collision, the 1m has a velocity 3v0, so its initial momentum is 3 times m times v0. So 3 times m times v0, that's the momentum of 1m before the collision. Assuming the collision happens really quickly. So at the end of the collision, the momentum changes to the mass times the final velocity. So it's 1m times 1/3 v0. So that's 1/3 m times v0. As for the velocity of 1m, before the collision, the velocity is 3v0. After the collision, the velocity is 1/3 v0. For the card 2m, before collision, it has the momentum mass times negative v, the velocity. So it has a momentum of the negative 2 mvo. So it's negative 2 mvo before the collision, and then after the collision, it has the same 1/3 vo for velocity. So the momentum is mass times the velocity, 2m times 1/3 vo. That would be 2/3 m times vo. For 2m's velocity, initial velocity is negative vo, final velocity is the same 1/3 vo, same as the 1m. Now let's look at the two-card system. The total momentum of the system is the momentum of the two cards added together. So these two added together gives us 1 mvo. And since the system's total momentum is conserved, it is the same 1 mvo before, during, and after the collision. So this is the graph for the momentum of the two-card system. We can also use the center of mass of the two-card system to represent the system. So the total momentum of the system equals to the momentum of the center of mass. Before collision, the total momentum of the system is these two added together, it's 1 mvo, which should equal to the momentum of the center of mass. And this momentum should be the mass times the velocity. If the center of mass represents the whole system, how much mass do you think we have? It would be 1m plus 2m. And the velocity will be the velocity of the center of mass. So we have mvo equals to 3m times the velocity of the center of mass. The m's cancel, so we can find the velocity of the center of mass to be vo divided by 3. So it is 1/3 vo. It's positive, that means it goes to the right. And because the total momentum in the system is conserved, that means that after the collision, the momentum is still the same amount, that means the velocity of the center of mass is still the same. And this works for before, during, and after the collision. So the velocity of the center of mass graph is like this. The same velocity the entire time. For this system, we have two cards on a horizontal surface. The cards' weights are cancelled by the normal force from the table. So if we can ignore friction, the net force on the system would be 0. That's why we can use conservation of momentum for this problem. When the net force on a system is 0, the center of mass of the system will have 0 acceleration. So constant velocity the entire time. The mass of the two cards has a 1:2 ratio. Their center of mass is closer to the heavier one, and the ratio of the distance is 2:1. This center of mass moves to the right at this 1/3 VO. Because the two cards stick together after the collision, the M, 2M, and the center of mass, they all move at that same velocity. They move together after the collision. Another thing is that because the momentum of the system is conserved, the decrease in momentum of one card must equal to the increase in momentum of the other card. Since the two cards have the same amount of change in momentum, the lighter card must have a larger change in velocity. In this case, the 1M, the lighter card, has a larger change in velocity than the heavier card. By the way, in this problem, we can say the momentum is conserved because the net force on the system is 0. Now, when would the net force on the system not be 0? For example, if there's a significant friction and the net friction on the whole system is not 0, then the net force on the whole system is not 0. Or, if a collision happens on an incline, then the net force on the whole system would not be 0 because the net force on the whole system would be the mg sine theta going down the incline. If the net force on the whole system is not 0, then we would not have momentum conservation. So for this collision, we cannot say the whole system's initial momentum equal to the final momentum.